Okay, good evening, everyone. So only two of you have
Good
joined.
evening.
Other peoples will not be coming. Sekat and Harit. Actually, I was waiting for them. That's why I have not started yet. Okay, no issue. Then we can start. Give me a minute. Okay, is the screen visible?
Yes.
Okay, so in last class, we have discussed Lewis dot structure. Then just I have written for resonance. I have not discussed yet. So today we are going to discuss this resonance. So what happens like, okay, let me explain this through simple example. See what happens like, have you seen the structure of benzene?
Yes, sir. So it has two resonance contributors to its DFS electrons.
Okay, so like there are three alternate pi bonds which are actually shifting the place due to conjugation. So rightly said, you will be getting two resonating structures, but there will be one structure which is actually showing the both two structure that will be known as resonance hybrid. Do you know about this previously? Tell. Okay, so first point I am discussing. So it is telling that a single Lewis structure actually cannot determine all the properties like bond length, bond angle, etc. So we need more than one structure to understand properties. So like you told that there can be like two resonating structure which can give the accurate information of all the bond angles, bond angle that can be formed. We'll be taking some examples so that it will be more clear that how the resonating structures are looking like. So here the first point is merely like single Lewis structure will not be drawing. Only single structure it will be not it will not suffice, but we have to draw more than one Lewis structure. So that structures are known as resonating structures. So this resonating structure are actually hypothetical structure. So this we actually made up in our mind only that these structures has to be formed, but they are not actually in real. They are just hypothetical. The real structure is the resonance hybrid. So if I talk about benzene, so benzene, if you are making three pi bonds separate and shifting their position, that will give you a hypothetical structure that will be resonating structure. But you have also seen like there a circle is made within six carbon atom. So that circle actually represent that double bond is actually present in along all the carbon carbon between all the carbon carbon. So that will be like your resonance hybrid. That circle that is representing that double bond can be present along all the carbon carbon between all the carbon carbon atom. So that will be your resonance hybrid. So what happens like if I am talking about resonance hybrid, that is giving information about all the structures. So that will be like more stable. Resonant hybrid will be more stable than the resonating structure. So there will be like difference in energy between the resonance hybrid as well as the difference in energy between the resonance hybrid and resonating structure, and that energy is known as resonance energy. So if I take the difference, like I subtract most stable resonating structure energy from resonance hybrid, so of course I will be getting, okay, can you tell me this resonance energy will be positive or negative?
Positive.
How you can say it is positive?
So because I feel resonance hybrid is more stable than the resonating structure.
So resonating hybrid is more stable, then it will be having less energy,
Then it's negative.
I mean to say, if resonance hybrid is more stable, it will be having less energy, less magnitude, and your more stable resonating structure is less stable, so it will be having higher energy. So you are subtracting less magnitude minus higher magnitude. So you will be getting resonance energy negative. So that's why we are telling that whenever we are getting resonance energy negative, I mean to say resonance energy is released, so it will be negative. It will be exothermic type. So your compound is getting more stabilized. That's why resonance actually stabilizes the molecule, because there will be resonance hybrid form, and resonance hybrid will be having lesser energy. So when you subtract resonance hybrid energy minus resonance more stable resonating structure energy, you will be getting negative value. Okay, understood this? Any doubt in this? So we can take some examples, then it will be more easily understandable. Okay, give me a 1 minute. Okay, so here one example I am taking of ozone. So ozone chemical formula we already know, it is O3, and when you will be drawing its structure by Lewis dot rules that I've already told you, you will be getting the structure like this one. Okay, so now I can see like if I give them this first, this is second, and this is third. So these are the three different atoms given, and if I calculate their formal charge, so that you will be getting like the first atom, if you calculate, you will get -1 formal charge. For second one, if you take, it will be getting 0, and for third one, if you calculate, you will be getting +1. Okay, that's why -1 +1, it neutralizes, and overall molecule is neutral. So technically this is double bond, this is single bond. So if I give this bond length x and this bond length y, so x should be greater than y, because x is single bond, so x should come greater than y. But this is wrong. Actually, what in nature found, bond length you are getting equal, x is equal to y. Okay, so that's why the first point written, that single Lewis structure cannot determine all the properties of bond length, bond angle, etc. So if you are drawing only single Lewis structure, so this cannot give you the entire information that your x is equal to y. According to it, x should be greater than y, but that is wrong. But x should be equal to y. So that's why we need more than one Lewis dot structure, or that is known as resonating structure. So first of all, you should know that resonating structure is drawn when you have conjugation. And conjugation means alternate position. Alternate position of negative charge, double bond, lone pair, like this one. So here you can see, like here you have alternate position of lone pair, single bond, pi bond. So pi bond and lone pair are at alternate position. So what is happening, like if you want to draw resonating structure in conjugation when they are in alternate position, lone pair and pi bond in this case, so there will be movement of electron density. So this lone pair will become pi bond, and this pi bond will become negative charge on this oxygen atom. Okay. Then again, in reverse direction, the movement can take place. That negative charge can become pi bond, and the pi bond formed here became again lone pair. So in this way, in both direction, movement of electron density takes place. So now we are going to resonating structure on seeing this conjugation. So first, along with the formal charge, if I draw, so I will be getting this structure. Here O minus, here O plus. Okay. So now this negative charge will go here, and this pi bond will become negative charge. Then we write like this arrow showing resonating structure. So next structure will be like this one, O double bond O plus. So this is your second resonating structure. Okay, so these two are resonating structure. Now again, negative charge can come here and pi bond can go there, so you will get the first one. So in this way, they both are interchangeable. So this is also resonating structure. And this is also resonating structure. Now, if I talk about resonance hybrid, so resonance hybrid should give the properties of both. Okay, so how it will be looking like? See, the pi bond is actually coming on both, between both oxygen atoms, here also and here also. So you have to draw like that one. That pi dotted pi bond you can draw. So it is actually coming in between both the atoms. And as well as you can see, negative charge is also shared between the two atoms. So sometimes it is on this oxygen atom, sometimes it is on this oxygen atom. But since it is shared between two oxygen atoms, so you have to write minus half, and this also minus half. So this will become your resonance hybrid. And this oxygen will be having positive charge. So in this way, you have to give resonating structure and resonance hybrid. Now I can take example of benzene. So benzene, you are having a structure like this one. So here you can see conjugation is of pi, single bond, pi bond, pi single pi. Okay, so if I give this bond length A, this bond length B, so technically if I am having only one Lewis dot structure, so B should be greater than A. But this is wrong. We are getting B is equal to A. B is equal to A. So if B is equal to A, then we are having one more resonating structure like this one, where the pi bond is coming like this one. Okay, so that's why you are getting the same bond length for B as well as A. In this resonating structure, double bond will be on A. In this double bond will be A. So basically, these are hypothetical structure. These resonating structures are hypothetical structure. They do not form. These are hypothetical structures. They actually do not form. So there has to be one resonance hybrid, which is representing all the resonating structure. So this will be a resonance hybrid. this is representing both structures. So in this way, in this by resonance hybrid, you can see A equal to B. And if you talk about resonance energy, so that you will be getting resonance hybrid energy minus most stable resonating structure energy. Okay, understood this? Any doubt in this? Resonating structure and resonance hybrid. Hmm?
No, sir.
Okay. So now next we are going to talk about bond order. Do you know what is bond order? Have you heard this term before?
Sir, I think bond order was the number of bonding electrons minus number of antibonding electrons by 2.
So where it is applied? From where you will get this bonding electron, anti-bonding electron?
So, like, I don't exactly remember, but I remember, like, it was a molecular orbital theory. I don't really remember. But
Okay. Yeah, very good. So this you are telling according to MOT. So MOT, there is a definite arrangement of electrons with respect to bonding orbital, anti-bonding orbital. So we arrange like that one. If it is less than 14, so there is different formula. Greater than 14, there is different formula. So one way of finding bond order is that one. You arrange them on the basis of MOT pattern. Then you calculate bonding electron, anti-bonding electron, then NB minus NA, that is number of bonding electron minus anti-bonding electron divided by 2. Okay. But that we are not going to use here because we are not going to talk about MOT. Simple bond order you can say, like if I do not want to apply MOT, just by looking the molecule, I want to say bond order. So what it will be, how it will be looking like? For example, can you tell the bond order of H2? Tell.
so, 1.
And for N2, just like you said, one for H2, for N2 it will be
So, 3.
and for O2,
2.
2. So this is the basic definition of bond order. So number of bonds, that is your bond order. Now we have to see like how we can see bond order when resonance is happening, because like in H2, N2, O2, you can simply see that there are perfect bonds are formed. But if I talk about resonating structures, for example O3, so O3 perfect bonds are not formed. So here you cannot directly say by seeing that these are the number of bonds, because partial double bond character is also coming. So partial double bond character you cannot take as one. So that's why in resonance resonating structure we have to see like how we can calculate bond order. Okay. So let me first write down this one. So bond order simply it is number of bonds between atoms. So if I write H single bond H, bond order I will get 1. If I write O double bond O, bond order I will get 2. If I write N triple bond N, so bond order I will be getting 3. So in this way bond order is written with respect to other molecules. Now if I am having the resonating structure, for example if I take O3, so one of the resonating structure you have to draw. So this will be like this one of the resonating structure. Okay. So the formula for bond order when you are actually seeing from resonating structure, it will be 1 plus pi upon sigma. 1 plus pi bond divided by sigma bond. So pi bond here you can see you are having only one pi bond. In sigma bonds you are having two. So you can write like this one. You have one pi bond and you have two sigma bonds. So bond order is coming to be 3 by 2. So in this way you have to. So next compound you can take CO3 2 minus. Okay, tell me of CO3 2 minus what bond order you will be getting. Can you tell by drawing resonating structures? Okay, CO3 2 minus I am telling. Next one you will be telling. So CO3 2 minus, if you draw its structure, Lewis dot structure, it will be like this one. CO3 2 minus. So you can see like its resonating structure will be like this one. You can see conjugation is present between pi single negative charge. So a negative charge will become pi bond and this pi bond can become negative charge. So you'll be getting the structure like this one. In third structure, this negative charge can become pi bond, this pi bond can become negative charge. So this will become like this one. Okay, so these are the three resonating structure. Now if I talk about bond order, it will be 1 plus pi upon sigma. So pi bond you can see here it is 1 and sigma bonds here are 3. So total you are getting 4 by 3. So that will be your bond order. So in particular resonating structure you will see total number of pi bonds. So you can see pi bond is 1 only and sigma bonds are 3. So you're getting 1 plus 1 by 3. If I draw its resonance hybrid, so resonance hybrid will be like this one. The negative charge is actually shared between 3 oxygen atoms. So 2 negative charge shared on 3 oxygen atoms, so it will become minus 2 by 3. And since the pi bond is also rotated between the 3, so you have to draw partial double bond character across the 3. Like this one. Here oxygen, here oxygen, here oxygen. So here minus 2 by 3, here it will come minus 2 by 3, here it will come minus 2 by 3. So this is because this is your resonance hybrid with respect to charges partial double bond character. So can you tell me what will be the relation between bond order and bond strength?
So more bond order, more bond strength.
And bond order and bond length?
So more bond order, less bond length.
Okay, very good. So this is an important concept. Bond order is directly proportional to bond strength. Okay, and it is inversely proportional to bond length, like you told. And if I talk about bond energy, so higher the bond order, you will be required more bond energy to break. Okay, so now I'm giving you two structures. One is I'm giving you PO4 3 minus. Another one I'm giving you NO2 minus. Please write their resonating structure, resonance hybrid, and calculate bond order. Okay. I'm giving you 5 minutes. So within 5 minutes, you can do it. Okay, done.
Yes.
Tell of PO for 3 minus, how you have done.
So the three resonating structures are P, double bond O, and three single bonds O, and each of the single bond O has a negative
Negative.
charge minus one, and like so, those are four structures, and the
Hmm.
bond order is 5 by 4.
Hmm. So in resonance hybrid, each oxygen will be having how much charge?
It's -3/4.
Yeah, very good. Okay, so let me draw this. So PO4 3 minus. So like you told, the resonating structure will be like this one. So each time if you make a resonating structure, this negative charge will be shifting and this pi bond will become negative charge. Likewise this one, likewise this one. Okay, so total, if I talk about bond order, I am getting here 1 plus pi here is 1, sigma bonds are 5, you are getting 5 by 4. Okay, and if I talk about resonance hybrid, so this will become like this one. Partial double bond character is coming. So here you will be having minus 3 by 4. Okay, so here you will be having 4 resonating structure. One this one and other from other 3 oxygen atom. So you'll be getting PO4 3 minus. Okay, tell of NO2 minus.
So N bonded to a double bonded O and single bonded O and single bonded who has a common has a -1. So there are two resonating structures, and the bond order is 3/2.
Very good. So if you draw it structure, you will first be getting N double bond O, single bond O minus. Now this minus charge can come here and this pi bond can shift on oxygen. So second resonating structure will become like this one. So we have 2 resonating structure you got. If you talk about resonance hybrid, so you get like this one, resonance hybrid, -1 by 2, -1 by 2. Bond order 1 plus, there is one pi bond and there are 2 sigma bonds, so you are getting 3 by 2. Okay, so likewise we can also make of SO4 2 minus. So for SO4 2 minus, you have a structure like this one, S double bond O, S double bond O. In last class in Lewis dot structure we have seen. So here you can see this negative charge can go on 4 oxygen atom. So -2 by 4, so minus half. So resonance hybrid will be looking like this one. Minus half, minus half, minus half, and minus half. And bond order, if you talk about, there are 2 pi bond and 4 sigma bonds. So you are getting 3 by 2. No, sorry, 6 by 4. Yeah, 3 by 2. Any doubt in this? So for you, homework is NO3 minus and CO2. These two are homework for you. Okay. And like CO3 2 minus we have already done. So you have to compare bond order of CO2 and CO3 2 minus. Okay, so next topic we are going to start is valence bond theory. So have you studied this? Have you know about anything about this valence bond theory? Amitesh, you say? Have you heard this before? Valence bond theory.
No, sir.
Soham, you?
No, sir.
Valence bond theory not taught in module 1.
No, sir.
Okay. Have you heard the term hybridization?
Yes.
Can you tell anything about it? Hmm?
So all I remember is that sp3 hybridization means single bond, sp2 hybridization means double bond, and sp hybridization means triple bond.
Okay. So here you told sp3. So this SR subshell that we have talked in atomic structure and chemical bonding in initial class. So if I am writing sp3, so what does it mean? Why we are writing sp3?
So I don't know how to explain exactly, but it's like one s hybridal and
Hmm.
three p hybridals. Like if you like them together and at like one energy level, then we get sp3.
So you mean to say you brought together one S you brought along with it 3p you bought and you intermix it. Then you got sp3. This you want to say?
Yes.
Okay, very good. So this is hybridization where intermixing of orbital takes place. Then you get sp3, and this sp3 orbital will make bond with another s or p or whatever. So this is hybridization. So hybridization will be studying, but after valence bond theory. So valence bond theory, like it does not talk about intermixing, but it talks about only the means how the bonds are formed when one orbital overlap with another orbital. For example, ss orbital, sp orbital, pp orbital means how sigma bond is formed by ss orbital by head-on collision between ss and head-on collision between pp. How pi bonds are formed by lateral overlapping of p orbital and p orbital. So when we are talking about bonds formed by single orbital, that will be like from VVT. But when we talk about bonds formed by intermixing of all the orbitals, that is given by hybridization. Okay. Okay. So let's do this VVT. Okay. So first write points. Valence bond theory. So first point, covalent bond is formed by overlapping of atomic orbitals. Atomic orbitals are s, p, d, and f. Okay, so this is the first point that I've already told you. The second point is there are two types of overlapping. First one is head-on overlapping. That is sigma bond. The second one is parallel overlapping. That is pi bond. Okay, so what I mean by head-on means like p orbital is dumbbell shape. So they are merging like this one. They are overlapping like this one. Okay, so one dumbbell is this, one dumbbell is this. So head-on overlapping. So that this will result in s sigma bond. But if I take two parallel p orbitals, this is dumbbell, this is another dumbbell, and they are making bond by lateral overlapping, not head-on, lateral overlapping. So this will result in pi bond. Okay, that's why the first bond is always sigma head-on. Another bond, if it is found, it is pi due to lateral overlapping. So this is the first difference that given by VVT. Okay, now the second point. So whenever any bond is formed, so there are some conditions. Okay, If that conditions are fulfilled, then only sigma and pi bonds are formed. For example, if I talk about p or p orbital, like this one, like this one. So each p orbital is having plus minus and plus minus. Okay, this plus or minus represent, you know, charge density, out of phase, in phase, like that one. So here you only that this thing you have to remember. You have to remember overlap will always take place with same phase. Okay, same phase, out of phase. What I mean to say, like we know that electron has wave character. Okay, so wave character. So the wave will be forming crest and trough. Okay, means they will be below the axis and sometimes they will be above the axis. So between, with respect to that one, suppose if I draw the wave pattern of electron, so it will be like this one. So this phase will be plus, this will be minus, again plus, again minus. So this is the plus minus represented. So one lobe will be plus, one lobe will be minus. What I mean to say here, overlapping will be only taking place between the same phase overlap. For example, plus will be overlapped with plus. Plus cannot overlap with minus. So if you are make so plus will be making bond with plus. In same way, if I take minus plus here and I make bond like this one, so this is not possible. Minus cannot make bond with plus. Only plus can make bond with plus. So first point you can write for requirement conditions. Same charge density overlaps. Okay, same charge density should be overlapping. The second important point for bonding is that one, there has to be proper orientation or proper alignment of orbitals. Means they cannot be misaligned because overlapping has to take place. What I mean to say, they cannot be like this one. One p orbital you are taking like this one p orbital you are taking like this one, and they will not align because there is no proper orientation. There is no area you are getting that can give you maximum overlap. Okay, either they had to be head on both in same direction in like this one, or either they can be like this one, same direction. So in this way overlapping takes place. Okay, so some important points about S subshell. So S subshell is symmetric in nature. Okay, so it is having only one phase because it is symmetric. Okay, so it is non-directional. Since it is symmetric, it is non-directional. It will not be having in a particular direction. So non-directional, symmetric, and this is getting merged with another symmetrical circle. So when they overlap, it will be looking like this one. So this will be head-on overlapping. And you can see, like, since it is non-directional, it is having same direction along all the 360-degree. So it will be non-directional symmetric and will always form head-on overlapping. Okay, that's why S orbital as always form sigma bond. With S and S, I've told head-on overlapping. I can also tell you between S and P. So this is S, and this is P. So you can see here head-on overlapping with plus and plus. So you're getting the sigma bond. So this example I have given for sigma bond between SNS and SNP. Now there are some examples for pi bond. So for pi, what I've told you, lateral overlapping. So lateral overlapping requires P and P, P and D, and between D and D. Okay, S cannot have pi bond because since it is symmetric in all the directions, so it will always have head on. From any direction orbital is approaching, it will become head on. But P and P can be taken parallelly and then you do lateral. Okay, so for first one example, I'm taking P and P. So this I've taken PZ and this also I've taken PZ. So here plus minus, here plus minus. So like I've told you, laterally they will be making overlapping. So when they make bond, so when overlapping is done, so after overlapping, it will be looking like this one. Okay, it is not becoming 1 minute. It will be looking like this one. So this we write as P pi overlapping because pi bond is formed by lateral overlapping and p orbital is involved in this. Okay, so let me give one example of PD. So this is PP, P now PD. So what I'm taking for P, I'm taking PZ, and for D, I'm taking DXZ. So if PZ, if I write, PZ will be looking like this one, and if I write DXZ, so DXZ, XZ direction like this one, and lobes are present between X and Z direction. This will be positive lobe, this will be negative lobe, this positive and this negative. Now you can see the positive lobe will come closer to each other and they will make pi bond. So after pi bond is formed, they will be looking like this one. So plus plus here, minus minus here. So this bond will be looking like this one. So this will be P pi D pi. Another example for D and D. So I can take here D XZ and DXZ. So it will be looking like this one. So they can make bond like this one. Okay. So when they will make bond, they will be looking like this one. So in this way, pi bond is formed. Any doubt in this?
No, sir.
So like pi bond is formed when the axes are always parallel to each other.
No. Which axis you are talking about?
So, no, so like the
Mm,
like
like there will be two axes, no? Suppose if I taking this BZ, so one axis is like this one, and one axis is like this one.
yes, sir.
No? So which axis you are talking about?
Sir, like there always be two axes which are parallel or like
It's not better to say in terms of axis, because if you take the example of P and D, so in D also there are two axes. So lobes are actually, you can say, are lateral to each other. Okay, they are not in head-on situation, but they are parallel to each other. And
yes,
if
sir.
you want to say in terms of axis, so it's better to say internuclear axis. Do you know internuclear axis?
No, sir.
So internuclear will be the axis, like I have taken PZ, no? So Z axis is internuclear axis. So that axis
Oh,
is actually dividing your whole orbital into two halves and passing
yes,
through the center of mass.
yes, sir.
Understood? So you can say internuclear axis is parallel, then pi bond is formed. And in case of P and D, so there you have to define the axis. Like you have to say Z axis of dxz and internuclear axis of p orbital, like this one. Understood?
Yes, sir.
Okay. So this general I have told. So again, in terms of orbitals, how we are using VBT means when electrons are present inside the orbital, then how the single electrons are making bond, that we have to see now. So some more postulates I am giving you. So postulates of valence bond theory. So first important points I've already told you: forming of overlapping of atomic orbitals. And second one is forming covalent bond. So this was introduced by Pauling and Slater. First point you can write: covalent bond is formed by overlapping of atomic orbitals atom should be very close. Okay, second point, two only half-filled orbitals with electron of opposite spin overlap. So there has to be two half-filled orbitals with single electron, and electron should be opposite spin. Then only they will attract each other. So like this one. So they will be attracting each other and the bond will be formed. The third one, overlapping should be less than 50%. Okay, so the area, if I'm talking about, the overlapping area should be less than 50%. If it is having high percentage, then there will be like repulsion will be happening between the electron density of overlapping. So that we do not want. We only want the bond to be formed. Fourth point, extent of overlapping directly proportional to strength of bond energy, strength of bond energy directly proportional to bond energy. Okay, the strength of bond will be higher, the bond energy will be higher, the strength of overlapping will be higher, and it will be inversely proportional to bond length. So it is same as the bond order. Okay, bond order is higher, strength of overlapping is higher. Fifth point, two types of overlapping which are possible. Axial overlapping, or head-on overlapping. That is known as sigma bond sigma is formed. Okay, so this I have already told you. Second one, so axial head-on is the same thing. Second one is parallel overlapping, or it is also known as side-wise overlapping. Or it is also known as lateral overlapping. So here pi bond is formed. Okay, sixth point. The overlapping orbital must have same sign. So this I've already told you. So these are the different phases of electrons. So plus will be merging with plus. So you'll be getting this one. Okay. So now we'll be taking some molecules. So these are the important points which I've told collectively. So some of the points I've already repeated. Okay. But they were like discussion type, they were not written at one go. So that's why the 6 points are written once again. No, 2 3 points are once again. The remaining points are new to you. So now what we are doing, we are going to write the molecules, and then we have to see that according to VBT how the bonds is formed. For example, if I write H2, okay. So in H2, what I have to do first, I have to write electronic configuration. So for hydrogen it is 1s1, for it is also 1s1. So you are having single electron. This you are also having single electron but opposite spin. Okay. So what will happen? Bond will be formed, and bond will be formed like this one, that S and S bond will be formed. So I already told you that sigma bond is always formed by S orbitals. So for that you are getting like this one, hydrogen hydrogen sigma bond, sigma 1s, sigma 1s. So if you make orbital, so it will be looking like this one, s orbital, like this one, like this one. Okay, so this is of hydrogen, this is of hydrogen. So when they make bond, like this bond will be formed. So you got sigma bond. Now if I talk about sp, so for that I can take example of HF. Okay, so first what I have told you, write electronic configuration, write hydrogen, fluorine. For hydrogen write 1s1, for fluorine write 1s2, 2s2, 2p, 5. So here you look at sigma 1s, sigma 2p. How you will be getting that one? The bond will be formed like this one. See, you have to write the electronic configuration of this p orbital. So if I write like this one, so p orbital, I know that p subshell is having 3 orbitals, px, py, pz. So px, py, pz. I have to give electron like this one, then like this one. So it is having p5. Now here, the opposite electronic configuration will be present like this one. This will make bond with this pz. So S pz, sigma for it is written 1s 2p. So 2pz it should be. Sigma 1s 2pz. So how this bond will be looking like? It will be like this one. So in this way, you got sigma 1s 2pz. This is your s, this is your pz. Okay, so now here if I am taking other halogens in place of fluorine, then how bond energy, bond length will be affected, that we have to see. So bond energy, if I talk about HF, HCl, HBr, and HI. Okay. So can you tell me the order of bond energy and bond length for these four hypovalence acids? You tell.
So I feel HI bond is the longest bond,
Mhm.
and so it has the least energy.
So you mean to say bond energy will be decreasing when I'm going from fluorine, chlorine, bromine, iodine.
Yes.
Okay, so yeah, it is right. So how I came to know this? So basically, like I told in BBT, how we are drawing orbital overlapping. So first you have to write orbitals. So if I'm going to write orbitals, so I will write in like for hydrogen it will be 1s always. The sigma bond will be formed between 1s and 2p here. For it will be formed 1s and 3p. For here it will be 1s and 4p, and for it will be 1s and 5p. So as you can see, like the p orbital is increasing. So overlapping area will be decreasing. Okay, so the extent of overlapping is decreasing. So extent of overlapping is decreasing. So that's why bond energy will increase. Sorry, bond energy will decrease. With less energy, it can be broken down easily. One another aspect of saying is that closer to nucleus, for that's why bond is strong. If it is very close to nucleus, your bond will be very strong. So it is difficult to break. So bond energy is higher. Likewise, you can see bond length. If higher orbitals are involved, so your bond length will be higher. So you will get HF, HCl, HBr, then HI. So as you can see, the bond orbital increases. So your bond length is increasing. Any doubt in this? You tell any doubt?
No, sir.
Okay, fine. So next we are going to take BF3 molecule. Okay, so there is one boron and three fluorine atoms. So if I write the electronic configuration of boron, So its atomic number is 5. So you get 1s2, 2s2, 2p1. And for fluorine, if you write, you get 1s2, 2s2, 2p5. Okay, so first we have to write the electronic configuration. So the outermost shell will be of the second shell. So 2s2 you have to write like this one. 2s2 2p1. It will be looking like this one. So p you have to make an entire orbital like this one, and then you have to make for this one 2p5. So here what you have to do, since the fluorine atoms are 3, so there will be like 3 single electron from fluorine side. Okay, but there has to be also 3 single electron from boron side, then only the bond can be made. But you can see here there is only 1 single electron. So what to do? You have to excite one of the electron to next orbital. So you have to go through first excited state. So if you write first excited state, you will be having like this one. So this is 2s and this is 2p. So now you got 3 electrons. And here you can say like this one. Free fluorine will be having 3 unpaired electron. It's better to use different types of orbital. For example, what I mean to say, if I write px, py, pz, so single electron is kept in pz here. So in second one, you can use like that one. You keep the single electron in middle one. Okay. So this will become your py and last one px. In this you keep single electron. Okay. So I mean to say the orientation will be, means the configuration will be like that one, that the 2 orbitals are fully filled and one is unpaired. The first one I have taken that pz, second one I have taken py, means I have taken the orbital in which the single electron is there as py, the other two will be px and pz. And third one I have taken a single electron is present in px, the other two will be py and pz. So how this will benefit? So this can be give you the 3 types of bond. For example, this s will be making bond with pz. Okay, so what is happening, like that will give you sigma bond. So first bond you got sigma 2s 2pz. Now here again you can see like there are 2p single electron with p single electron here. So again this can give you head-on overlapping. Okay, so this will become your py. So sigma 2py 2py. Okay, now the third one that is left. So this can become py, this can become px, and the third one will be pz. So px can make bond with px. Third one you got sigma 2px 2px. So in this way, you got three varieties of sigma bond. Suppose the structure will be looking like this one, BF3. So three sigma bonds are there, and you are having three types of bond between S and S sigma bond and between P and P sigma bond. So why I have taken like different PX, PY, PZ in fluorine, so that I can align them with the axis of P of boron. So PY will be aligned with PY, PZ will be aligned with PX will be aligned with PX. Any doubt in this? How single electron are combining to give you bond? Tell.
No, sir.
Okay, then do for H2 and tell me. Then I will be telling you that whether it is right or wrong. I'm giving you 5 minutes. Okay, do for this H2O. Okay, tell how you have done water.
So it is a sigma bond between 2py and 1s and 2pz and 1s.
Okay, tell step by step how you have done. Like I've done step by step.
First I wrote the electron configuration of water, that is 1s square, 2s square, 2p4, and hydrogen, that is, hydrogen, that is 1s. Then 2p4, the 2p4 on oxygen, it has 2 unpaired electrons, and there's 1 unpaired electron per hydrogen, so we can connect those. So we get 2py and 1s and 2pz and 1s. Both of them are sigma bonds.
Okay. So like in the previous one, I have written px, py, pz. So have you used a specific orbital for that one?
Yes, sir.
So what we can write for sigma means along with the orbital, sigma 1s 2px, let's say.
2py and 2pz.
Yeah. Okay, fine. Thank you. Okay, so let me write again. So hydrogen and oxygen. So 1s1, like you told. So there will be 2 hydrogen atoms. So it will be also having 1s1, one single electron, one single electron. In oxygen, you have in 1s2, 2s2, 2p4. So when I write the electronic configuration of 2p4, so I will be getting like this one. Okay. So I can assign any direction to this one, p by pz, let's say. So here you can see one electron can bond with this electron and one electron can bond with this electron. So both, it will be like S bond always from sigma bond, I have told you. So it will be like sigma 1s 2p. And here I have taken 2py. So sigma 1 is 2py and sigma 1s 2pz. So these two sigma bonds will be found. So this example I have taken of sigma bond. In sigma bond, you have to write electronic configuration like this one. Then you have to check for alignment for sigma bond. They have to be same direction. Then you have to tell that how many sigma bond and what variety sigma bond is formed. Okay. So now let's take some example of second type of bond, that is sidewise overlapping or parallel overlapping. Okay. So here the parallel direction thing that I've already told you. The two orbitals has to be parallel, and after they are parallel overlapping is formed. So here what point you have to remember, first bond is always sigma bond, then make pi bond. Okay. So first always try to align the orbitals like that one, that you get sigma bond. So it's better out of the all purely you take one pz. Okay, so this is common practice. Out of x, y, z, z is always used for sigma bond, and the other two will be perpendicular to it. So you can form pi bond from x and y. Okay. And second point you have to remember. Okay, can you tell me out of sigma bond and pi bond, which one will be stronger?
So sigma bond.
Why?
Sir, I don't know. I read somewhere.
Tell the logic also, no? think some point. What point you can think that sigma that makes sigma bond more stronger than pi bond?
Sir, I feel because the extent of overlapping in sigma bond is more than the extent of overlapping in pi bond, so it's stronger.
Why extent overlapping is higher for S?
Because it's like head-on overlapping for sigma bond, while for pi bond it's just lateral.
Yeah. So like head-on overlapping when takes place, so there will be more area covered in overlapping. But if you see lateral when they are parallel and when they are overlapping, the area covered will be less. So that's why extent of overlapping is higher for sigma bond. That's why sigma bond is stronger than pi bond. So you can write sigma bond is stronger than pi bond. Okay. So one example we can take. So one example I can take of O2. So to give me the complete picture that how along with sigma pi bond is formed. So first what we have to do, we have to write the electronic configuration of both oxygen atom. So this will give you 1s2, 2s2, 2p4, and this will give you also 1s2, 2s2, 2p4. Okay, now I have to write electronic configuration of the last subshell orbital. So it will look like this one. Here it will look like this one. Okay. So what I have told you, like there are two unpaired electron and here two unpaired electron. So one will be merging with this one and one will be overlapping with this one. But one you have to form sigma always. So for that purpose, what I told you, like Z axis is normally taken for head on. So you take this as PZ, this also as PZ, and perpendicular to it there will be two PX or PY. So that you can take as PX and PX. So that will be responsible for pi bond. So like this you can see. So it will be looking like this one. PZ you have taken like this one. So they are giving head-on overlapping. And perpendicular to it, you are having PX. So they will be giving you head-on overlapping. So Z axis, this axis will be Z here, and this will be Y. PY, and this will be PZ. So the bond you can think of here, it will be sigma 2PZ and 2PZ. And as well as pi will be of 2px and 2px. You can make from y also. Sigma 2py, sigma 2py, no issue. So this, sorry, I have made it, py should be px, since I used x here. So pi bond between px and sigma bond between py. So in this way, bond is formed. Any doubt in this? That how pi is formed along with sigma?
Sir, we can take like Y also.
Yeah, y
Or-
also you can take. But for sigma, you take z. For other pi, you can take x or y.
Yes.
So sigma 2pz, 2pz, sigma 2py, pi 2py, 2py will be also correct.
Yes.
Okay, so I'm giving you, please try to make for N2. Then we'll be discussing that how it is made. Okay, I'm giving you 5 minutes. Make for N2. Okay, tell how you have done.
So the electron configuration of nitrogen is 1s squared, 2s squared, 2p3. So
Mhm.
there's a sigma bond between 2pz and 2pz. There is a pi bond between 2py and 2py. There's also pi bond between 2px and 2px.
Very good. Okay, so let me explain this. So into the first step that you write electronic configuration for both. So that will be like 1s2, 2s2, 2p3, 1s2, 2s2, 2p3. So 2p3 will be looking like this one. Single electron will be there here like this one. Okay. So what I told you, like you take it as px, py, pz. This also px, py, pz. But make one sigma bond has to be always formed. So here only p orbital side word. So sigma bond will be between pz and pz. So that will be your sigma. The other two will be pi bond. That will be between py and py. Another one will be also, sorry, pi bond. Okay. So now you can easily see 1 sigma 2 pi. So the variety of bonds we are getting here is sigma 2pz, 2pz, pi 2py, 2py, pi 2pz, 2pz. And how it will be looking like this one, it will be looking like. So this will be getting for pz. The other two are perpendicular. So they will give you py. And the third one, that will be also perpendicular. So this will be giving the pi bond with this one. Okay. So this is your pz. This is say px, and this will be py. So in this way, your bond will be looking like this one. So if I talk about individual p orbital, so this is pz, this is px, and this I have taken as py. Okay, so x and y can be perpendicular, no issue. There's one question I'm giving, then we can wrap up. So you have to tell number of sigma bonds and pi bonds. The first molecule is H2O. Second is NH3. Third is C2H2. Fourth is C2H4. Fifth is CH3COH. Sixth is C2CN4. Okay. I'm giving you 5 minutes. Please try this. Then we'll be ending up class. Okay, done. That is very simple. Who's going to tell?
Sir, 2 minutes.
Tell. Okay, so take this as homework. We'll be discussing in next class. Okay, is that fine?
Yes, sir.
Yes, sir.
Okay, so I'm wrapping up this class here. Whatever doubt you have, you please tell me in next class. We will be discussing it. Okay. Thank you, everyone.
Thank you, sir. Bye, sir.
Bye, sir. Thank you, sir.
Thank you.